The last of the intermolecular forces that I want you to understand is the ion-dipole attraction. And the reason that it's separate from the rest of the intermolecular forces is because it's not technically an intermolecular force. Now, when we say intermolecular force, the word molecule corresponds to covalently bonded molecules only. And the name ion-dipole attraction, by definition, is the attraction between an ion or multiple ions in an ionic compound in any polar molecule. For this example, we're going to use sodium chloride right here, and our friend water here. We have to remember that in an ionic compound, the ions are attracted to each other, and although the formula NaCl corresponds to one sodium ion and one chlorine ion, the ions clump together in zillions rather than just in one NaCl unit. This lattice structure, if you think about how this is arranged, this is what you see, or what you're putting on your French fries, for example. Is just a zillion of these units attracted to each other. Water is covalently bonded. If you remember from the previous video, we have to remember that water has a partially negative end and a partially positive end. Any polar molecule has that. For the larger molecules, we talk about it more like partially positive regions and partially negative regions if those regions aren't on the ends. I know it's a small difference here, but since we're dealing with small molecules, we'll talk about the ends of the molecules because they are charged. And for sodium chloride, the smaller purple ions here are positively charged sodiums, and the green larger ions are for the negative chloride ions. Going back to atomic structure, if an atom has an electron taken away, like in sodium, the size of that atom decreases. And if an ion or an atom has an electron added to it, the size of that ion increases. So here, the larger one is going to be the negative ion, and the smaller one is going to be the positive ion. And so to continue to learn about ion-dipole attraction, well, it's an attraction between the ions in the ionic compound and the dipole, or either end of the water molecule. And the question that I want us to think about right now is, how will the water molecules orient around the ionic compound? Because we know that when we put salt in water, it dissolves. Why? Well, we know theoretically, or we're taught that the water molecules split apart the ions in the ionic compound, but ion-dipole attraction is the why behind why that happens. In any sample, if you imagine taking a few grains of salt and adding it to a glass of water, you would have, gigazillions molecules of water and maybe just zillions of NaCl units. Immediately, the water molecules are going to surround that chunk of salt. However fine the salt is, if it's in one huge lump, the water molecules are going to surround around it. If it's split up into much finer pieces, the water is going to orient or surround all of them and pull it apart until all of the ions in the chunk are gone. So we've got this one water molecule. The question is, where is it going to land and how is it going to orient itself? Well, we said before that this end of the water molecule, the oxygen part, is partially negative. And we said that this purple one was the positive ion. And so there's an attraction there. Now the question is, what happens next? Well, we said that there were gigazillions of water molecules in the cup of water, and here they are. And for instructional purposes, by gigazillions, I mean 6. Just to illustrate the purpose, we want to show what happens when the water molecules surround the salt crystal. Again, we said that, for example, the red oxygen would be attracted to the purple positive ions, and then the white hydrogens, the positive ends of the water molecule, would be attracted to the negatively charged chloride ions. And so if you can imagine this happening at the gigazillion scale, these water molecules are basically going to carry away these ions until they're completely separated, and that every ion is floating by itself but surrounded by water molecules. The difference between us seeing the salt undissolved in the water and us seeing nothing at all, the point at which it's a solution, is that when it's a solution, all of the ions are separate. When we think about the properties of substances, one of the properties of salt is that it's a solid. When it's dissolved, it's no longer a solid. Part of it has to do with the structure of that crystal, those ions being closer together. And this is the final result. When the ion-dipole attraction between the water molecules and the ions in the ionic compound run their course, when you think about what happens, say if you were to put that salt in the water, mix it around, all the while the water molecules are pulling ions off of that crystal and evenly spreading out inside that mixture. And when it's totally dissolved, this is what you would see if you had those atomic goggles. You would see the positive sodium ions and the negative chloride ions separated out, and the part of a bunch of water molecules surrounding each one. I chose 3 here. That is not the magic number. How many water molecules that surround an ion depends on how large that ion is. The larger the ion, the more water molecules are required to surround the ion. When you think about the solubility of ionic compounds, if an ionic compound is very soluble, it means that it doesn't need a lot of water molecules to surround each ion to stay dissolved. If it's not very soluble, it needs more water molecules to surround each ion. In general, the bigger the ion, the less soluble it is. I'm not going to go too much into depth about that here because that's not the purpose. But in general here, when an ionic compound dissolves in water, this is what happens. And this is to illustrate the point of an ion-dipole attraction, which again isn't a genuine intermolecular force, but it's something that can explain how substances interact with each other, which is valuable.